Hi folks, we are on the Unit 3 Day 6 lesson and we're going to be talking about the intersection of lines in R3. So we're going to be talking about a few different things. We're going to talk about how lines intersect with other lines and also how lines are going to intersect with planes. So this is going to be kind of pulling together all of the work that you did in the first half of Unit 3, where we were looking at different forms of the equations of lines and planes, and now doing some manipulation with those equations and trying to solve to identify what the intersection or lack of intersection in a number of different situations is going to look like. Sorry. So first of all, I've got some diagrams here, and if we talk about intersection, normally we talk about that, and our first picture is probably this case. So if you wanted to talk about an intersection of a line and a plane, I think most people would kind of have this visual as their first instinct, that you've got this plane pi, and remember we represent that with the parallelogram, and you have a line that cuts through the plane and it's going to intersect the plane at one point. So there's one point on that plane where the line passes through, so there's one individual point that lies both on the plane and on the line. So I think that that kind of visually is what people most often think of. We have to kind of remember, however, that there's not necessarily, when we talk about an intersection, that's kind of a theoretical, like, is there an intersection? So solving for the intersection of a line and a plane where there isn't an intersection, or maybe where there's an infinite number of intersections, that can also happen. So there's two other cases here that maybe don't look, especially this one, it doesn't look like an intersection because it actually doesn't intersect. There's 0 points of intersection here. This would be if the plane lay here and the line was parallel to the plane but not on the plane. So this line would not intersect the plane at all, and there would be no points of intersection. And the third and final case here is if the line actually lay on the plane. So if the line is actually right directly on the plane, then there's infinite points of intersection, and we would have, when we go to solve for that, we're going to see that all of the points on the line are also contained on that plane. So there could be 0, infinite, or 1 point of intersection when we look at the interaction of a line and a plane. Okay, just to clarify what we're talking about in terms of points of intersection, that is the point when the x, y, and now z, because now we're in R3 and looking at that third dimension, when those values are the same point exist both on the line and on the plane. So this one point or multiple points would satisfy both equations. So that's what we're really looking for. And because we have so many different forms of the equation, it is going to kind of depend on what form you have, how you're going to do this. So the first thing I would recommend is, and I think that this is a pretty good rule just overall when we're doing intersections. With intersections, you always want the equation of your plane to be in Cartesian or scalar form. So for intersections, the equation of the plane always in Cartesian. Now I have, with these examples, I've got the equations of the plane always in Cartesian form, but you could be given a question where it wasn't in Cartesian form. You would then have to convert that vector or parametric equation of a plane into a Cartesian equation, by doing the cross product and finding the d value before you went ahead with the intersection. So we know a lot of different ways of solving for points of intersection or intersections of functions or equations, and most of them involve substituting something into another one, or some kind of elimination where you're adding or subtracting multiple equations. Now, there isn't an equation of a line that can look like this, that we would be able to do some sort of elimination. That's not something that we have, but there is a form of a line that we could substitute in for the x, the y, and the z. And that would be the parametric form of the equation of the line. So I'm going to take that equation of the line and convert it to parametric. Because here we would get the x, y, and z all in terms of one parameter of t. So we would have these all in terms of one variable. So x is 1 plus 2t, y is negative 6 plus 3t, and z is negative 5 plus 2t. And we know that t can be any real number. So what we're going to do is to sub these in for our x, y, and z into the equation of the plane and see if we can solve that for t. So 4x minus 2y plus z minus 19 equals 0. And my x value, I had 1 plus 2t. Y was negative 6 plus 3t. Z was negative 5 plus 2t, and then I have minus 19 equals 0. So I'm just going to go through and solve this for t. Once I get a t value, I can go back to those parametric equations and put it in to find the x, the y, and the z. So 4 plus 8t plus 12, careful with my negatives here, minus 6t minus 5 plus 2t minus 19 equals 0. And how many t's do I have? 8 minus 6 is 2, plus 2 more, I have 4t. And then 4 and 12 is 16, minus 5 is 11. And then minus 19, I get negative 8 equals 0. And then bring that 8 over, divide by 4, t is equal to 2. So we know that this intersection will happen with a parameter of t when that t is equal to 2. So we can just take that, like I said before, and sub it back in for the parametric equations for x, y, and z. So 1 plus 2 times 2, x is 5, y is negative 6 plus 3 times 2, so y is 0, and z is negative 5 plus 2 times 2. Z is negative 1. So the point of intersection is 5, 0, negative 1. So none of the math is particularly tricky. It's just a matter of thinking about what this intersection means and how we solve for intersections. And then also being able to convert between the different forms of the equations of lines and planes. So that's example number 1. Example number 2 is very similar, except already we're actually given the equation of the line already in parametric. This is kind of a big lesson with a number of different examples, so I'm kind of making this a little bit easier. You've got the equation of the line in parametric form, you have the equation of the plane in Cartesian form, which is exactly how you want to have these. Typically you may need to do a bit more work than this and actually have to convert from one form to another, like especially if you had that in a vector form for the equation of the plane, it's a bit more work to get it into Cartesian. But for now, we are pretty well set up here. X plus 4y plus 2z minus 4 equals 0. And then I'm just going to take the parametric equations for x, y, and z and substitute them in. So x is 2t plus 4 times y, which is 1 minus t, plus 2 times z, which is negative 4 plus t, minus 4 equals 0. And then expanding, collect like terms, 2t plus 4 minus 4t minus 8 plus 2t minus 4 equals 0. Solving for my t's, I have 2t minus 4t is negative 2t, and then plus 2t. So this is a little bit tricky. I have 0 t's. I don't really have a t to solve for anymore. And that's okay. We're going to kind of keep plugging through here. Here I have 4. Minus 8 is negative 4. Minus 4 more is minus 8 equals 0. So I come up with negative 8 equals 0, and I have no t's to solve for. So which of the 3 cases do you feel like this might be? Negative 8 really never equals to 0. So this tells us that there are no solutions. There's no solutions, no values of t where negative 8 will equal 0. So that means the line is parallel to the plane. Okay, so you can, in fact, check. And the way you would check to see if a line was parallel to the plane, you could take the direction vector of the line and the normal vector and do the dot product of those two and see if they were perpendicular. So if the normal vector of the plane was perpendicular to the direction vector of the line, then that would say that the line is parallel to the plane. But we don't necessarily have to do that because we can follow this same process. And if we get something that's just nonsense, like negative 8 equals 0, you know that that never happens. So that's the no solutions case. You could, maybe I'll just show that quick. The line, if we did that here, the line can be written as 0, 1, negative 4, just kind of pulling out these position and direction vectors. Then we'd have 2, negative 1, and 1. So the direction vector A is 2, negative 1, 1. And we would check A dot N, and knowing here that the normal vector to the plane is 1, 4, 2. So that we can check A dot N, which is 2, negative 1, 1 dot 1, 4, 2. So 2 times 1 plus negative 1 times 4 plus 1 times 2. 2 minus 4 plus 2 is 0. So the normal to the plane, remember that's the one coming up perpendicular to the plane, is also perpendicular to the line. So that means that the line is parallel to the plane because this one is perpendicular to the plane and perpendicular to the line. So the plane and the line must be parallel to each other. This check is not an alternative to solving here. If you checked and got this equal to 0, you still don't actually know which of the 2 cases it's going to be, because it might be this case here where it's parallel but not on the plane, and it might be this case here where it's directly on the plane. So checking that dot product isn't sufficient to decide which of the 2 cases that is. It just tells you that there's not going to be an intersection, and a distinct intersection. It might be the infinite points and it might be the 0. You don't know. So that's why I like this way better of just doing the math and seeing what pops out for the t value at the end. The third example here, again, I've tried to make this a little bit easier, that we've got our x and y and z in parametric, and we have an equation of a plane in Cartesian form. So I'm going to sub those in. We've got again, finding point of intersection of line and plane. And this one, I think we're going to get one where it is that third case. So our x was -4 plus 3t from the line, minus 2 times the y value is 0, minus 3 times the z value of t, plus 4 equals 0. So here, -4 plus 3t minus 3t plus 4 equals 0. And 3t minus 3t is just gone. -4 plus 4 is just gone. So I get 0 equals 0. Now remember, in the last one we got -8 equals 0, which that's never ever true, so there's no solutions. But 0 equals 0, that's always true. It doesn't matter what t is, this is always true. So this is always true, no matter what t is. So this case is that the line is on the plane because it's always intersecting. Regardless of the t value, the point on the line is also on the plane. So infinite points of intersection, the line is on the plane. Okay. So that's the three cases, kind of visually and algebraically, of what can happen when you try and find a point of intersection of a line and a plane. In the next video, we're going to look at the point of intersection of two lines.